Now let's do the exercise problems. Let me start with exercise problem 10.1. Monochromatic light of wavelength 589 nanometer is incident from air on a water surface. What are the wavelength, frequency and speed of reflected and refracted light? Refractive index of water is 1.33. So there is monochromatic light of wavelength 589 nanometers. So there is this water surface. I will do 10.1 now. There is water surface, and it's monochromatic light hits here. Okay. So what happens now is that part of it reflects from the water surface, and then part of the light refracts through the water. So this could be something like this. Reflection takes place, and here refraction takes place here. Okay. So now the question is, what are the wavelength, frequency and speed of this light? Reflected and refracted. Refractive index of water is 1.33. So mu of water with respect to air, obviously, right? So which is equal to 1.33. So here the lambda is 589 nanometers. So let's talk about reflection. Where is this reflection taking place? It is taking place in the first medium itself, and refraction is through the second medium. So you see that wave comes, then gets here, and then gets reflected. Will the speed change? The speed will not change, because they are traveling in the same medium. When it gets reflected, the wave is traveling in the same medium, which is medium 1. So you know that V, the speed, is equal to n into, or I'll put f, it's better, f to lambda, right? So V will remain the same. Then what happens? Here I'll consider this to be air or vacuum, either is almost the same. So speed of light in air or vacuum is roughly 3 into 10 power 8 meter per second, and that is equal to the frequency, and the lambda is 589 10 power minus 9 meters. Okay. From this you can find the frequency. Now this is 3, this is almost, 589 is almost 600. So I can say that it is 3 into 10 power 8, so divided by, I'll say 6 into 10 power minus 7. This should be fine, right? I've taken 200s here. So 6 and 10 power minus 7, roughly, approximately. This is 1 by 2, and this goes up, so that becomes 10 power 15. So 0.5 into 10 power 15, or 5 into 10 power 14 hertz. So this is the frequency of light. And what is the wavelength? The wavelength will not change, because the wave is traveling in the same medium after reflection. So nothing happens there. But what about refraction? Even here, V is equal to f lambda. But you see, the speed has changed. You don't have the same speed in the second medium. So you need to find that. So 1.33 is actually 4 by 3, right? That's what I'm going to use. So what does the refractive index mean? Refractive index of water means the speed of light in air or vacuum is divided by the speed of light in water. That's what, right? So we can say, and this is equal to 4 by 3. And you know C, so you can find V. So what's V? Water is actually 3C by 4. 3C by 4, so it'll be 3 into 10 power 8 by 4. So this is 9 by 4 to 10 power 8. That's the speed. Okay. So what do we know? We know that the frequency does not change when the wave travels from one medium to another medium. So this frequency will not change, but the wavelength will change. So if I were to use the same equation here, what have we got here? My V double is 9 by 4 into 10 power 8 is equal to, F will not change, so roughly 5 into 10 power 14 hertz, and then this lambda. So in here, so that gets you lambda is equal to 9 by 20. This is 10 power 8, this is 10 power, then you'll get 10 power 6. That's what you'll get. Okay, like that. So when you bring it down, and that becomes lambda equal to 10 power 6 meters. So that gives you 4.5 10 power minus 7 meters. Well, if I multiply that by 100 and divide it by 100, then I will get 450 10 power minus 9 meters. So this is equal to 450 nanometers roughly. So the same wave which had a wavelength of 589 nanometers in the first medium now has a wavelength of 450 roughly 450 nanometers. I say it's roughly because this is not exact. I will approximate it. So roughly 450 nanometers there. So you can see that the wavelength has changed, has become smaller here, but then the frequency will remain the same. Hope this is clear to you. Okay, as a side note, I want to say this. While doing this problem, we said part of the light will be reflected and part of the light will be refracted. And you may ask, how would it even happen? To understand this, I will give you the example of a mechanical wave, like a sound wave. Then you can understand light, in that light. Okay. It's like this. See, when I speak, then what happens? I create a disturbance in air. Then the disturbance travels, not the molecules. When I speak, the molecules in my mouth don't reach the speaker. So they just push the molecules next to my mouth, and then those molecules push the molecules next to them, and then they push molecules next to them. Likewise, this disturbance that I produce in my vocal cords is getting propagated in the medium, the air medium, and then it comes and hits the speaker, and from there something else takes place. You can convert that into electrical signals and electromagnetic waves and transmit, and all those things will happen later, okay, for you to receive whatever is being said in this video. But that is beside the point. So the point is, when I speak, then the disturbance travels, and then I'm able to push the molecules near my mouth, and they push the molecule next to them. So likewise, if this happens continuously, and what happens is that then there are air molecules here. Okay, this is surface. The surface I got. Let's say I have this book here. So when I speak here, I push molecules, and then they go and hit this book. Right? Finally, these molecules will be pushed. Okay, pushed here. And when they hit, the air molecules hit the surface, in this case the book I've taken, then what happens is they will get reflected. Okay, they will be rebound. As they rebound, then they will hit the molecules next to them, and those molecules will hit the molecules next to them, and those molecules will hit the molecules next to them, and likewise the sound wave travels. But notice one thing. When the air molecules came and hit these the molecules, when the air molecules hit the book, the molecules in the book, they get disturbed, right? So they came and collided with this molecule. So what will happen? This molecule will push the molecule next to it, here. Okay? So then there are molecules here in the book. Okay? These are the molecules in the book, and they will get disturbed. They will disturb the molecules next to them, and they will disturb the molecules next to them. So you see, this hit, this collision is now propagated through the book too. And in fact, the speed will be greater here actually. Okay? Sound travels faster in the solid medium than in this medium, in a gaseous medium. So this will be the sound waves will travel faster in the book, solid medium. That which is slightly different from what we saw as far as light was concerned. So you can see that as they hit here, the sound wave gets reflected from the surface, and then the sound wave is also refracted through the surface. The vibration of the molecules, the top layer of the book will disturb the molecules in the bottom layer. So then this is how sound is getting transmitted through solids and liquids and gases. So if this can happen in sounds, then it happens in light, because light is a wave. You can assume that light comes and hits here, and the same thing happens here. Then like if this can go through, if it's a transparent medium, then part of it will get reflected. So after colliding, these would impart some energy, right? They'll lose some energy, impart some energy to these particles, and then they'll be left with less energy than before. So they'll go like that. Okay. So this energy and this energy would be equal to the incident energy. So something similar is happening with light wave. The light wave comes and hits here, and part of it is transmitted, part of it is reflected. You can see it. I hope you are able to see this. You can see my shadow, or rather, I should say like my reflection here from this glass, because light goes and hits, and part of it is reflected and then it's coming back to you, and at the same time you will be able to see something which is beyond this glass. So that is refraction. And if someone stands outside, then they will be able to see me standing here. So part of the light which is going from me is getting reflected back to you, and part of it is going through the glass. What is the shape or the wavefront in each of the following cases? That is 10.2. Light diverging from a point source. So if you have a point source, light will diverge from here in all directions. So you can expect the wavefront to be spherical in nature. So if you want to find, if you want to find the points at which the value of the field will be the same, the electric field and the magnetic field will be the same, then they will be equidistant from the point source. So a spherical wave would be formed again around the point source. I think we discussed that already in the class, but let me say it again. So light diverging from point source will be spherical. The wavefront of the light diverging from point source. And B, light emerging out of a convex lens when a point source is placed at its focus. Well, that's easy. So you have a convex lens, and then let's suppose that this is the focus. If I have a point source here, then notice light will travel like this and will travel in all the directions. We are not bothered about that, we are bothered about only those things, the light that is hitting the lens from the source. And after hitting the lens, then they will go straight. So, if they are parallel, then they have to be plane wavefront. Okay? So, the wavefront is plane wavefront. C. The portion of the wavefront of light from a distant star intercepted by the Earth. Okay, you have Earth here, and there is a distant star. Then whatever light that is coming from here must be parallel, because it's a distant star, it's so far away, so the light will be almost, the rays, light rays will be almost parallel. Okay. So this will also be a plane wavefront, either from the sun or from other stars, whatever you see from a distance. It needs to be a plane wavefront. Now 10.3 A. The refractive index of glass is 1.5. What is the speed of light in glass? Speed of light in vacuum is 3 into 10 power 8 meter per second. Then B. Is the speed of light in glass independent of the color of light? If not, which of the two colors, red and violet, travels slower in a glass prism? Okay, let's start with the first part, which is this. The refractive index of glass is given, it's 10.3. The refractive index of glass is given to be 1.5. Then they want you to find the speed of light in glass. We know that. So if this is a glass surface and if this is vacuum or air, then so light will travel with some speed here, and they'll call it as C, and then this would be V. So the refractive index of glass is actually C by V, and that is equal to 1.5. So what's V? V is equal to C by 1.5. What is C? 3 into 10 power 8 meter per second divided by 1.5. So this will cancel. 2, so you will get 2 into 10 power 8 meter per second. So that's the speed of light in glass. The speed has to be less than the speed of light in vacuum or air, because the refractive index is greater than 1. Second, is the speed of light in glass independent of the color of light? If not, which of the two colors, red and violet, travels slower in a glass prism? Well, you may have noticed this. Okay. Suppose I have a glass prism, and then light hits here. It's white light. This is a combination of all the 7 colors, and infrared and ultraviolet. Let's not bother about that. So let's talk about visible light. So this is the white light is hitting here. So it has all the colors now. all the waves have come together to form this white light. Then what happens is that then you get a pattern like this. Okay. So note here, this is red and this would be violet. So Vibgya is what should happen. So note that if all of them had the same refractive index, or if all of them travel in this medium with the same speed, then they would refract by the same amount. But note this, red refracts only so much and violet refracts this much. See? So clearly the colors don't travel with the same speed. If they travel in this medium with the same speed, then the refraction will also be the angles will also be the same, but you see that there are different angles to it. So the refractive indices for different colors are different in the same medium. So this is what actually gives rise to what is called as a chromatic aberration we talked about in lenses, where they don't focus because light travels in with different wavelengths, different frequencies will travel with different speeds in this the other medium. Okay, so here is what is happening here. Then to answer this question, is the speed of light in glass independent of the color of light? No. If it is independent of the color of light, then they will all be refracting with the same angle, but they don't. If not, which of the two colors, red and violet, travels slower in a glass prism? Well, which will travel slower? So clearly, you can see that this is an odd one. Okay? The light should have gone like this. This is an odd one. But then it is bent. Red bent. This is theta red. Then this is theta violet. Okay. So for the first one is theta red, the whole thing, and the last one will be theta violet. You can see that violet has bent more. So if something bends more, then that must be traveling slower. Think about it. This is the path without any bending. Then if it bends, like if it travels almost the same distance, let's say this is the distance. Let's say like this point, I'll call this as A and this is B. A takes certain time to reach this place, I call this as A dash. At the same time, B should be traveling inside the medium. And if it is slower, then it will travel this distance. So clearly, when I connect this, the wavefront, notice that this is going to be smaller than that. But then, if this is faster, then it will cover a long distance, right? So only if it is slower, then it will cover this distance. Then, notice that the bending will be more. The bending will be more. For this, the bending will be slight. So only if it travels slower, the bending will be more. Likewise, if you take here the violet light, which is part of the white light, has bent more than the red light, which means that violet is slower in this medium. So velocity or speed of violet must be less than the speed of red. Hope you understand this. Problem number 4, 10.4. In a Young's double slit experiment, the slits are separated by 0.28 millimeter and the screen is placed 1.4 meter away. The distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. Determine the wavelength of light used in the experiment. So you have Young's double slit experiment, it's 10.4, which means that you have a slit here and then you have a slit here and then you have the screen here. So what happens is that you will have a central bright spot, right? So this is bright here, and then there will be dark, and then you will have a bright here. The first bright. This is BC, central bright spot, and then B1. And after some distance, you will have a bright spot again, B2, and then B3, maybe here, and B4. So bright spots. And between these two bright spots, then you will have a dark spot. So bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. Go on like that. Okay. So you know that this is D, and then this is small d, and given all that. Right? So what this asked? The slits are separated by 0.28 millimeter. So this B is equal to 0.28 millimeter. And the screen is 1.4 meter away. This is equal to 1.4 meter. Okay? And the distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeters. So this is center BC from here, and the fourth is here. This distance is measured to be 1.2 centimeters. Okay, I'm not drawn them to scale. And clearly I can't draw them to scale here because you need to see those points. So, but this is just 1.2 centimeter, 1.4 meter, and then this is 0.28 millimeter. Okay? So understand this. Then determine the wavelength of light used in the experiment. Well, it's so what do we know? First of all, we know that the bandwidth, beta bandwidth is equal to lambda d by d. Okay, so this is bandwidth. What have they given you? They given 1.2 centimeters. So 1, 2, 3, 4. So 4 bandwidth. So from bright, dark, bright. So this is 1. And dark, bright, 2. Dark, bright. So this is 1 bandwidth, 2, and 3, and 4. There are 4 bandwidths in 1.2 centimeters. So B, beta, is equal to 1.2 into 10 to the power minus 2 meters. So divided by 4. Give you 0.3 to 10 to the power minus 2, or 3 to 10 to the power minus 3 meters, or 3 millimeters. So that's the bandwidth. 3 millimeter is the bandwidth. Then put this in this equation. So lambda d by d, lambda is what they're asking you to find. So lambda, so d is 1.4 meters divided by the separation is 0.28 millimeters, which is 10 power minus 3 meters, and this must be equal to 0.3, rather I should say 3 into 10 power minus 3, 3 to 10 power minus 3 meters. Okay. What can I do? I can do something. I can say that lambda is equal to 3 into 10 power minus 3 into 0.28 10 power minus 3 divided by 1.4. So what can I do now? Well, I can I can multiply this by 10 and divide that by 10. So I'll get 2.8. I'll just multiply this by 10 and divide this by 10, so I don't change anything. So I'll get 3 into, I'll just plug these things together. 10 power minus 6, right? 10 power minus 6 into 2.8, so divided by 1.4 to 10. So this would be 2. Then 10 power minus 1 will come there. So lambda is equal to 6 into 10 power minus 7 meters. Or if I multiply this by 100, divide that by 100, so let's do the 6 into 10 power minus 7 into 100 by 100, because I'm trying to convert that into nanometers now. So that gives you 600 into 10 power minus 9 meters. So lambda is equal to 600 nanometers. This is how we do this problem. Problem 10.6 is an important problem. Many times questions have been asked based on this model, so pay attention to it. A beam of light consisting of two wavelengths, 650 nanometers and 520 nanometers, is used to obtain interference fringes in a Young's double slit experiment. Find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometers. It is part 1. And then the second one is, what is the least distance from the central maximum where the bright fringes due to both the wavelengths coincide? Okay, so we need to understand the problem first. What is asked? You are doing Young's double slit experiment. So it's a beam of light which consists of both the wavelengths. Okay, it's a combination of both. But let's do it one by one. If I send one wavelength, then this will become monochromatic light, and that will form an interference pattern on the screen. And that wavelength will have a bandwidth. Now, if I switch this off and use the second light with wavelength lambda 2, then that will also form interference patterns on the screen for the same slit distance, separation, and the distance between the slits and then the screen. Everything else remains the same, but you are changing only the wavelength, and this will also form an interference pattern. And it will have its own bandwidth. This bandwidth will not be the same as the previous bandwidth, even though you have used the same setup. Small d, the distance of separation between the two slits, remains the same in both cases. Capital D, the distance between the slits and then the screen, remains the same in both cases. The lambda is changing. The lambda is changing, then the bandwidth will change. So you will get one bandwidth for red light and a different bandwidth for a green light, and yet another bandwidth for a violet light for the same setup. So something like this is happening. Then what he is saying is the incident light as both the wavelengths, which is same as doing this experiment separately for both the waves. But you are combining now. Okay. Let's see. So this is 10.6. So this is slit 1, and this is slit 2, and this is D, the distance of separation, and then you have the screen here. And let us suppose that this is where you form the central bright spot. It's the central maximum. This will be the same for both the wavelengths, because you know the central point in the Young's double slit experiment will always be a bright spot. So this is going to be bright whether I use lambda 1 or lambda 2. But bandwidth will be different. Maybe you have a bandwidth like this. This is beta 1, and then you have same beta 1, beta 1 for all this. So the bandwidth will be something for beta 1. But when I use a different wavelength, second one, and maybe that will have a beta. This will also have the central maximum here, and then this could have a different beta. Okay, see, like that, something like this, and then the fourth one maybe coincides there. Okay. So you have 1, 2, 3, which have 1, 2, 3, 4. Okay. Let's say to be better. Okay. So then the fourth one may coincide with the third one or something, because this has this bandwidth, third, then fourth. Okay, and this coincides with the blue. The fourth red coincides with the third blue. So we are asking you which one would be the minimum distance at which this will happen. The central maximum, it will always happen, because red will fall here and blue will also fall here, the center. So the coincidence happens here. They both coincide. But once you go away from this point, then you know, depending on the bandwidth, you can have different spots. But then it's like an LCD, right? So after some time, then this must be equal to this one. Then again, whatever happens here will happen there. And from then on, you wouldn't have these bright spots coinciding for some dots, and after that, you will have the coincidence again. The same thing will happen here too. Yeah. So this is a problem. So what is asked will do. A beam of light consisting of two wavelengths, 650 nanometers and 520 nanometers. So I'll call lambda 1 as 650 nanometers. And then lambda 2 is going to be 520 nanometers. Then find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometers. Yeah. So 1, 2, 3. So they first want you to find this distance for 650 nanometers. So we know bandwidth, right? So bandwidth for lambda 1 would be lambda 1 to d by d, because d and d will be the same for both, and this will be your d. We know this. So everything else is given. First of all, this problem has not given you d and d. Only lambda 1 is given. So d and d have not been given, so you can't proceed. Okay? So if d and d are given, you go and do this. But it's not given now. Can't do anything now. So the first part, A, cannot be done. Insufficient information. So what was the second part? Can you do? Yeah. What is the least distance from the central maximum where the bright fringes due to both the wavelengths coincide? Like that. Okay. So for both of the fringes to coincide, what should happen? This distance must be the same for both, right? So let us say in that distance where this point where both the fringes coincide, I take this length as y. Okay. So what is y? Y must be equal to number of fringes in one multiplied by bandwidth, beta 1. And y must be the same for the second one, number of fringes in lambda in the second wave multiplied by beta 2. This should happen. So, for both if y is the same, then they will coincide at y. So, I can say that n1 beta 1 equal to n2 beta 2. What else do you know? n1, what is beta 1? Beta 1 is lambda 1 d by d. That must be equal to n2 to lambda 2, the same d by d, because the apparatus does not change. Okay, so d and d can cancel, so small d and small d can cancel. Then from this you can say that n1 lambda 1 must be equal to n2 lambda 2. So n1 by n2 must be equal to lambda 2 by lambda 1. So what is lambda 2? That is 520 nanometers, 10 to the minus 9 meters. So divided by 650 into 10 to the minus 9 meters. So this will go away. And again, I can cancel this. And what am I left with? I'm left with something. 52 by 65. So n1 by n2 is equal to 52 by 65. So if I divide it by 13, then I would know that 13 into 4 gives me 52, and then this is 13 into 5 gives me 65. So I can remove this. So n1 by n2 is equal to 4 by 5. Okay. So 5n1 will be equal to 4n2. So what happens is n1 will have the 5 bands. Okay. Let's say if we take n1 will have 1, 2, 3, 4, 5 from the center. Let's say this is the center. Let's say central maximum, right? 1, 2, 3, 4, 5. It must be equal to n2 into 4. So we'll get 1, maybe then 2, maybe 3, 3 here, and then 4 here. Okay? So this is the n2. So, 5 of n1 will be equal to 4 of n2. So the fifth band of n1, lambda 1, will match with the fourth band of n2. So that's about it. Hope this is clear to you. To 10.7 now. In a double slit experiment, the angular width of a fringe is found to be 0.2 degrees on a screen placed 1 meter away. The wavelength of light used is 600 nanometers. And what will be the angular width of the fringe if the entire experimental apparatus is immersed in water. Take refractive index of water to be 4/3. So what is asked, so you're doing a double slit experiment and you get the fringe width. Okay, the fringe width is given in angles. Okay, well, it's like this. First of all, this is 10.7. So I have S1, S2. I have the screen. Let's say this is my central bright, central maximum now. Then I can have the next maximum there. So this is BC and this is B1. What is done here is this. Okay, so they've given you this angular width theta, and they've done that in air. Now they want to do the same experiment in water. Then they're asking you to find out what would be this theta when you perform the same experiment, same slits, same distance in water. Okay, first of all, what is the angular width? Okay, we know what is this basically. This is the bandwidth, right? So bandwidth is given by this expression lambda d by d. Okay, so notice here, what is it is like this, right? It's like if bandwidth is this width. Okay, so this is the formula you already got. So look at it like the segment length. Okay, it is like this, right? So like if you take a arc length, okay, it's almost the same, right? So you have r, and if you have theta, then what is s? S is r into theta, theta in radians here. So likewise, this beta is going to be equal to, what is r here? R is d, right? So d, r is d. So d into theta. So this theta, if you compare these two now, d is here, d is here. So theta in radians must be equal to lambda by d. Okay. So if this remains the same, if d remains the same, the distance between the slits, this is d, right? If this remains the same, and this also, d also remains the same, then theta will depend on the wavelength, lambda. But what did we say? When light travels from one medium to another medium, the wavelength will change. Why? The speed changes. Because the speed changes in the second medium, the wavelength will also change. So the frequency will remain the same, but the wavelength will change. First medium, C is equal to same f lambda 1, let's say V1, better, right? And second medium, V2 is equal to same frequency but the lambda different. If I do V1 by V2, then I get this. So what is V1 by V2? First medium, second medium, that's going to be the refractive index of the second medium with respect to the first medium. So that is given, that's going to be 4/3. It's given in the problem. And F will cancel, so lambda 1 by lambda 2. That's what you get. Okay, so now, can you express lambda 2 in terms of lambda 1? So what is lambda 1? Lambda 1 was in, say, air or vacuum. And vacuum or air. Same. This lambda 2 is in water. Okay. So lambda 2 is going to be equal to 3 lambda 1 by 4, 3/4 of lambda 1. So I'm going to use this information here. So what was theta 1? That is the angular width in the first medium, which is air. That was equal to lambda 1 by d, using this expression. What's going to be theta 2? Same thing. It's going to be lambda 2 by d, and that is also equal to 3 lambda 1 by 3 by 4. Okay. So what it is. And what is 3 lambda 1 by d? That's actually theta 1, right? So theta 2 is equal to 3/4 of theta 1. But what is theta 1? It's given 0.2 degrees. Theta 1 is 0.2 degrees, and theta 2 would be 3 into 0.2 by 4 degrees. So theta 2 is equal to 0.6 by 4 will be 0.15 degree. This is much easier to do this way rather than converting this degree into radians and then finding the radians and theta 2 in radians and finally converting it back into degrees. So first you do it like this, handle that in equations with symbols, and once you get the final equation like this, then just put in the numbers and we'll get all of them. We'll get the right answer in the last second, the last step of this clear to you. You can ignore question 10.8 and 10.9 because they are about polarization. So let's move on to 10.10, the 10th problem. Estimate the distance for which ray optics is a good approximation from an aperture of 4 mm and wavelength of 400 nanometer. Okay. So it's 10.10. So estimate the distance for which ray optics is a good approximation for an aperture of 4 mm and wavelength of 400 nanometers. So the aperture A is given 4 mm or 4 into 10 power minus 3 meter, and the wavelength lambda is given to be 400 nanometers. 400 nanometers are 400 into 10 power minus 9 meters, or 4 into 10 power minus 7 meters. Okay. So we know that the ray optics could be used till the Fresnel distance, and beyond the Fresnel distance you cannot use ray optics because the wave nature of light will be predominant after that distance. So till the Fresnel distance you can use ray optics. So that's the limit, right? And what is the Fresnel distance? We have seen that the Fresnel distance z f is equal to a squared by lambda. So what's a here? It's 4. So 4 into 10 power minus 3 the whole square. So divided by 4 into 10 power minus 7 meters. Okay. So this is what you got here. So this is going to be meters squared and this will be meter. So meters. So it will be 16 into 10 power minus 6 by 4 into 10 power minus 6, 4 into 10 power minus 7 meters. So this will be 4, and this will be 1, so it goes up. So then Fresnel distance is 40 meters. So when I have an aperture of about 4 millimeters, this is the aperture. Light goes through this aperture 4 millimeter. Then for 40 meters, I can use ray optics. I can just talk about rays and images, objects, and keep drawing lines from the object to the image. And this can happen till 40 meters. So very safe in using ray optics, even though light is a wave. Hope this is clear to you.